having a chiral will rotate plane polarized light to the left, or it will rotate plane polarized light to the left or to the right. We simply cannot tell. And so we have to find a way of being able to distinguish between two pairs of enantiomers. Let's go back to the example of 2-butanol. I'll write the OH will be pointing up, let me change the orientation. The OH, I'll make the H to pointing up and the OH to pointing away from us. Okay? Whilst the two carbon chains are in the plane of the paper. So the H is above the plane. The OH is going down the plane. And so like we said, if we call this 2-butanol, we will not be absolutely right, because we can draw a mirror image of this molecule, and that mirror image would also be 2-butanol. But we just learned that these two molecules will rotate plane polarized light in different directions. These molecules will rotate plane polarized light in different directions. So if that's the case, how do we distinguish between the two molecules? 3 people provided the most comprehensive description of how to distinguish between these two. And so that system that they propose has come to be known as the Kahn, Ingold, and Prelog nomenclature. Or system. Sometimes you hear about CIP system or nomenclature. CIP system or nomenclature. Well, their system is simple, and that is, one, if you want to distinguish between two pairs of enantiomers, or you want to name a molecule that has a chiral center, so that its enantiomer will not have the same name as itself, we use two letters from the words from the Latin. R for rectus, which is right, and S for sinister, which means left, to distinguish between them. So for two enantiomers, one will be R, one will be S. R for rectus, right, S for sinister, left. However, like I said, this does not tell us whether it is going to rotate the plane polarized light in the direction alpha or minus alpha. All that we want is to be able to distinguish between the two of them by a certain name. The rotation of plane polarized light is experimentally determined, and so we simply cannot do that. So let me say it again, that the R and S notation does not tell us whether it's going to be alpha or minus alpha in terms of the rotation of plane polarized light. That is important to distinguish. So how do we implement this system? This system says that one, identify the chiral center. Okay. Now that is easy. That's not the crux of the issue. Now, once we've identified the chiral center, the first thing is to assign priorities to the groups attached to the chiral center. And the priorities are assigned in order 1, 2, 3, and 4 from largest to the smallest. So the smallest group is always given the lowest priority, which is 4. The largest is given the highest priority, which is 1. And here, largest is in terms of atomic weight, atomic number first, before molecular weight. So you look at the groups that are directly attached to the chiral carbon. It's important to bear this in mind. These are the groups that are directly attached to the chiral carbon. And we start with the atom. Okay? So even though molecular weight becomes important, we start with the atomic mass or isotopic mass of the individual atoms directly attached to the chiral carbon before we go on to the next. So if we are not able to distinguish or assign all the priorities based on the first atom, then we go to the next atom, then we go to the next atom, then we go to the next, until we are able to distinguish between the two groups. So for 2-butanol, there is a hydrogen, there is a carbon, there is an oxygen, and there's a carbon that are directly attached to the chiral carbon, which I've indicated by asterisks. And so if you look at this carefully, oxygen has a higher atomic number than carbon, and carbon has a higher atomic number or atomic mass than hydrogen. Okay? And because of that, we will assign priority 1 to the oxygen, which is the hydroxy group. Now, we have 2 carbons directly attached, so we can't distinguish between them, but they are both bigger than hydrogen. So hydrogen will be our lowest priority. So we assign that as 4. So lowest priority hydrogen is assigned 4. Highest priority oxygen in the form of hydroxyl is assigned 1. Now we have to be able to distinguish between the two groups which all have carbon as their direct attachment. So like I said, if we are not able to assign based on the first atom that is directly attached to the carbon, then we go on to the next one. With the methyl group, all the other atoms are hydrogens. On the ethyl group, we have hydrogens, and then we have carbon. So, because the hydrogens are the same, what we do is that on the methyl group, the next atom is a hydrogen. On the ethyl group, the next atom will choose carbon. And because carbon is bigger than hydrogen, we say that the ethyl group has a higher priority than the methyl group. And so we assign priority number 2 to the ethyl group, and then we assign priority number 3 to the methyl group. So where the functional groups remain the same, then the various molecular weights can be used, as in this instance. The ethyl group is bigger than the methyl group, and so the ethyl group gets priority over the methyl group. But we always do it systematically, looking at the atoms that are directly bonded to the chiral center and the next atoms that are directly bonded to that atom until we are able to assign all the priorities. Great. Once we have been able to assign the priorities from 1 to 4, there is another exercise that we need to do to be able to determine whether the molecule is an R or an S. Okay? Whether it's an R or an S. So now we've been able to assign all the priorities. So let's determine it. Now the next guideline says that arrange the molecules so that the lowest priority, the least priority, is pointing away from you. All right. In the three-dimensional carbon bonds, we saw that the bond with the broken wedge is the bond that's pointing away from you. Okay? The bond with the broken wedge is the bond that's pointing away from you. And so the second guideline or second rule says that we should arrange the molecules or the atoms around the chiral carbon such that the atom or the group with the least priority is pointing away from you. Okay? Now, what it means in our drawing or in our structure, the hydrogen, which is the least priority, is pointing up, while the oxygen or the hydroxyl group, which is the highest priority, is pointing down. What it means is that we have to do a rotation We have to do a rotation to be able to bring the hydrogen to the bond that is pointing down and the hydroxyl group to whatever direction. Here, all that we need is that we rotate it so that the hydrogen or the least priority group is pointing away from you. In doing so, there are what we call, and this is not a guideline, the allowed rotations. Okay, there are allowed rotations. Not every rotation is allowed. So that once you carry out an allowed rotation, then you haven't changed the molecule. Every time you carry out a rotation that is not allowed, the molecule would have changed. The molecule would have changed. Now, because carbon-carbon single bonds have free rotation around the carbon-carbon bond, what it means is that for as long as we keep one position fixed, we can rotate the other groups in an allowed fashion. Carbon-carbon single bonds, carbon other atom single bonds generally have free rotation about a carbon single bond. And because of that free rotation, what has been observed is that if we fix the position of one of the groups, then every rotation we do is allowed because of the free rotation about the bond. So in our structure, 2-butanol, we want to bring position 4 to where position 1 is. And so let's hold position 2 fixed. Okay? So we are going to maintain position 2. We are not going to change it. So let me just use position 2 here. This is position. We all know what position 1 is, so let me not put in that. Now if we hold position 2 fixed and we rotate in the clockwise direction, so we are fixing position 2, we are not changing it, but because we want the hydrogen to come to where the hydroxyl group is, I'm saying that we fixed position 2 and then we rotate the rest of the molecule in any direction since it is allowed once position 2 is fixed. And that means that position 4 will now come here, position 1 will go there, and position 3 will go there. So what I've done is that I have fixed position 2 and I've done a clockwise rotation based on my screen to move position 4 to position 1, position 2, position 1 to position 3, and position 3 to position 4. So I have carried out a clockwise rotation, but because I have fixed the position of 2, this rotation is allowed. So now, once we have the lowest priority groups or lowest priority group pointing away from you, which is what we have in the current configuration. The next guideline is to count the priorities 1, 2, and 3. If they are clockwise, then that molecule is assigned the R. If 1, 2, 3 is in counterclockwise, then we assign it the S. And here it is only the 1, 2, 3 that we are going to count, because the fourth or the lowest priority is pointing away from us. So if we go back to our structure, we are going to ignore the position 4. So let me just erase. Oops, sorry. Okay. Now let's count them. If we count 1, 2, 3, this is counterclockwise. And so this molecule is assigned the S. This molecule is assigned the S. This molecule is assigned the S. What it means is that this structure here is the S isomer. The S isomer. And so in writing the name of the molecule, we put S. Okay? We put S in front of it. We put S in front of it to distinguish it from the other enantiomer. Okay? We put S in front of it to distinguish from the other enantiomer. So for example, and we need to specify what carbon is the chiral center. We need to specify which carbon is the chiral center. So we know that the chiral center is on carbon number 2, and on that carbon number 2, it's an S isomer that we have. So we put that in bracket, and then we put a dash, and this is 2-butanol. So this is 2S 2-butanol. This molecule we have is 2S 2-butanol. We can also have the 2R 2-butanol. Let me just draw the 2R 2-butanol for you. So the molecule here will be the 2R 2-butanol. And you can clearly see this is priority number 1, this is priority number 2, this will be priority number 3, and this will be priority number 4. And since the lowest priority is already pointing away from us, when we count 1, 2, and 3, it is in the clockwise direction. So this is the R enantiomer. This is the R enantiomer. I hope that is easy for everyone. So assigning the R and the S is very easy. It's very easy. And once You start by assigning priorities, and that is by looking at the atomic mass or atomic number of the atoms that are directly attached to the chiral center. Those are the first options. If that is not enough to distinguish between the atoms, we go to the next atom, the next atom, the next atom, until we are able to distinguish between any groups that still remain. Once we've done that, we look at how these groups are arranged. If need be, we do an allowed rotation by fixing the position of one of the groups whilst rotating the others. By so doing, we do an allowed rotation. And we make sure that the lowest priority group is pointing away from us. And once the lowest priority group is pointing away from us, we count the priorities 1, 2, and 3. And if these are in clockwise direction, then we assign an R to the molecule. If the numbers 1, 2, and 3 are in a counterclockwise direction, then we assign S to the molecule. Then we assign S to the molecule. Let's look at a few scenarios where assigning priorities may present some difficulty or challenges. If, for example, you have multiple bonds. So let's say I have C, C, Y. Okay, how do we arrange this? CCY in the Kahn-Ingold Prolog system simply means you have a C that is attached this way. These are the original ones. It means there is the Y, which is directly attached to this carbon, and there is a Y that is directly attached to that carbon, and then there's a C. So this is how a C double bond Y is interpreted in the CYP nomenclature. What it means is that if I have a C triple bond Y, okay, that would mean have this C bonded to whatever unit that is there. It means this C is bonded to a Y and bonded to another Y and bonded to another Y. So there are 3 Ys that are directly bonded to that carbon, and the other Y also has C bonded to them. So this is how the CYP notation works. This is how the CYP notation works. What it means is that if I have a CC double bond, it will have a lower priority than a CC triple bond. The reason being that we always look at the atoms directly attached to the carbon. So assuming this is the bond directly attached to the chiral center, then this carbon would have 1 carbon and 1 carbon, okay? And this will have another carbon. And that will have another carbon. Depending on which group is there. Let's just say this one is an R, just so that we can distinguish between them. On the other hand, for a CC triple bond, okay, this is the bond to the chiral center. Let me put asterisks here and asterisks there. This will have one carbon and another carbon, all because of the triple bond here. And this carbon will have the same. And so there are more carbons directly attached to the next carbon bearing the chiral center than the preceding one. And this is how we are able to distinguish between chiral molecules that are attached to the chiral center, molecules that are attached to the chiral, especially those that contain the same functional group. The same functional group. It's always important to bear in mind that a CC double bond would have a lower priority than a CC triple bond. Several examples of this are given in your slides, so you can take a look at these carefully, work out all the examples so that you can become perfect at identifying or determining the configuration around chiral centers or chiral carbons. And so by configuration, I mean the R or the S. So you come across R and S configuration or R and S notation. R and S configuration or R and S notation. So bear these things in mind. So let me go over some of the concepts that we've talked about. We've talked about chiral molecules as compounds containing carbon that has 4 different groups attached to it. Okay? We talked about enantiomers as chiral molecules that are mirror images of each other, but they are non-superimposable. They are non-superimposable. They relate to each other like the left and the right hand. We talked about stereoisomers that are not mirror images of each other as being called diastereomers. Diastereomers. I mentioned that if a molecule contains a chiral center and it's able to rotate plane polarized light, then that molecule is said to be optically active. That molecule is said to be optically active. I want to emphasize that it is not every molecule that contains a chiral center that is optically active. Some molecules that have chiral centers are not optically active because they contain what we call a center of symmetry or a plane of symmetry. A center of symmetry or a plane of symmetry. We have just found, or we just looked at how we can distinguish between 2 pairs of enantiomers by using the Kahn-Ingold Trelog system, or CIP system for short. We said that you assign priorities to the chiral the molecules that surround the chiral center by looking at the atomic masses or atomic number of the individual atoms directly attached to the carbon, which is the chiral center. And if for whatever reason that is unsuccessful, you go to the next atom that are directly attached to that carbon until you are able to distinguish any group of atoms. I mentioned that carbon-carbon double bond has a lower priority than a carbon-carbon triple bond, and so forth. I mentioned to you that for a pair of enantiomers, they will rotate plane polarized light to the right or to the left. And so one of the pairs will rotate the plane polarized light to the left, the other will rotate a plane polarized light to the right. So if the other one rotates to the left, the other enantiomer will rotate to the right. And it's because if you take the electromagnetic spectrum, or you take light in particular, they are in all directions. So if you're able to isolate just one of those directions and you pass that through your molecule or a solution of your molecule, they will interact with the light and change its direction by a certain degree or certain angle called alpha. And what we said is that if one enantiomer rotated to the left, that enantiomer rotated to the right, to the same magnitude but different directions. That remains the single most important difference between pairs of enantiomers. Other behaviors or other difference between enantiomers is the way they interact with chiral compounds and chiral resins, chiral molecules, etc. But that we haven't looked at yet. So we will look at that when we get to that point. It is important to mention at this point that to be able to compare different compounds and how they interact with plane polarized light, we want to make sure that we standardize this experiment. We want to make sure that we standardize this experiment. So we define a parameter we call specific rotation. We define a parameter we call specific rotation. And we give a specific rotation also as alpha, but we always put it in the square bracket. Typically, we specify the temperature at which the experiment was conducted and the source of light. Okay? Plus the source of light, because if we use different type of light, we would get different results. We will get different result. So alpha in square bracket with the specific rotation is given as the alpha, which is the observed rotation, divided by the concentration, and here it has to be in gram per milliliter, multiplied by the length, length of the cuvette, or what you call the cell, the container in which you put the sample, the length of that container is what I'm talking about. It's called a cell, and it has to be in decimeters. So when you do an experiment, whatever rotation you observe, that is what is called the observed rotation. If you divide that by the concentration of the material you used times the length of the cell that you used, that gives you a specific rotation that can be compared to others. So for as long as all the other experiments that you are going to compare with were carried out using the same temperature, okay? And then here, we the sodium D line, so most of the time you see a D, so 2 pairs of enantiomers.